So hello everyone, this is lecture 2 for the classical mechanics, or we can call it classical physics. So yesterday we discussed up to here the stable equilibrium. I told you the difference between the stable and the unstable equilibrium and how to find the points of equilibrium points, means just putting this potential, and this is nothing but potential energy. Here in the classical mechanics we call it as potential, the potential energy. Okay, so we put it as 0 and then we find the values of x. Then those points give us the points of equilibrium. Then we find they are stable or unstable by just taking the second order derivative, and if it is greater than 0 then it will be stable and minima, and if it is less than 0 then it will be maxima and the unstable equilibrium point. So we were here about the small oscillations with the, if I was saying that if it is at unstable equilibrium point, means at a stable equilibrium point, and we gave us some energy, extra energy, then it's gonna have a small oscillations, and unbound motion means it will have the turning points. So this was a small energy delta E. Then now we need to find the frequency of this oscillation. This type of question is asked in the previous years, that what will the frequency if it is disturbed with a little bit in energy delta E. So that energy will give the extra kinetic energy, because at this point kinetic energy is 0. The extra energy will goes to the kinetic energy. Now the potential, if we displace it by x displacement, then Vx equal to Vx naught plus x minus x naught. Here x naught will cancel out, it will be Vx again. So if we expand this, so just remember this formula for expansion, don't need to go in the depth of the derivation. It will be Vx naught plus delta V upon delta x at x equal to x naught, x minus x naught, then it upon 1 upon 2 factorial plus del square V by del x square, then x minus x naught ka whole square. The next term will be 1 upon 3 factorial at x equal to x naught, x minus x naught ka whole cube, and so on. So see, if displacement is very small, then oscillation will be very small, and this difference is very small, x minus x naught. So for the higher terms, then cube and the 4 terms, then that will be tending to very much small, and they will be 0. So that's why we didn't take those terms, and here we just consider these 3 terms, 1, 2 and 3. Okay, so we know at x equal to x naught, this delta V upon delta x is 0. Okay, so this term will be 0, it will be neglected, means will be eliminated. Now the second term, at x equal to x naught, if it is this one, then we know for the stable equilibrium point the second order derivative is less than, not less than, it is greater than 0. Only then we will have the local minima. So this term at x equal to x naught will be positive, so we call this whole term as some k. Okay, so it will be Vx naught plus k by 2 x minus x naught ka whole square. Okay, these higher terms are neglected, so this whole equation will be reduced to this. Vx equal to Vx naught plus half k x minus x naught ka whole square. Okay, we here k equal to this, and at x equal to x naught, del u by del x is 0. I already told you this, and k is some positive quantity. Now see, we know what is the formula for force. Force is nothing but partial differentiation of v with respect to x, means gradient of v. So if you differentiate this, it will give you, this will be 0 because it is constant, and when you differentiate this, it will be k x minus x naught, and force will be minus k x minus x naught. So you can see this expression for force, it is for the harmonic oscillator system, minus kx type, and from here if you find the acceleration, then it will be a equal to this divided by m. Now this is the acceleration for the harmonic oscillator type systems, so we'll call it as omega square x. You know the acceleration is minus omega square x for the harmonic systems. Now after comparing this, omega square equal to k upon m, then omega will be root, this k is this del square v by del x square at x equal to x naught divided by m. So this will be the frequency of the small oscillations after disturbing the particle from the stable equilibrium point. So remember this formula, there are many questions asked from this. okay, directly. So let's see about the unstable equilibrium point. So when this happens, means this kind of potential we have, now this point is unstable equilibrium point, and if some extra energy is given, delta E, then see it will came out to be here. And now if particle is disturbed, then if it is going this side, then potential energy is decreasing, then kinetic energy is increasing, and it will goes to increasing. So the particle will never come back, and it will go to the infinite. It will be unbound motion, and same from the left hand side. So that's why we call it as unstable equilibrium point, because it don't wanna achieve its this position again. Okay, it will leave it forever. This is unbound motion. So at this point slope will be 0, and the second order derivative will be less than 0. Okay. At this point kinetic energy is 0, and when you give some energy, then all energy convert to the kinetic energy, and that's how I already told you this thing. A system is said to be in a unstable equilibrium if a small displacement of the system from the equilibrium position results in an unbound motion. So this was the thing I told you. Now this is also I told you localized maxima. This should be less than 0 at x equal to x02. Now let's see some questions. They are asked in the previous year questions. These are the previous year questions. So let's see first question. A particle of unit mass moves in a potential this. So potential is given, mass is given 1 unit, and A and B are positive constants. So we need to find the angular frequency omega of small oscillations about the minima of the Vx. So the same question as we solved this. So omega is nothing but del square V by del x square at x equal to x naught. And x naught is what? It is the equilibrium point or the stable equilibrium point. So how can you find this? First you will differentiate it with respect to x. You will find the points. Those are the equilibrium points. And those points you will find the stable equilibrium point. And at that point you will find this del square V by del x square, and you will divide with mass m. Then you will get the answer. So stable equilibrium point you will get as x naught equal to b upon a 1 by 4, and second order derivative will give you 8a. This is positive, that's why you are getting minimum. And after substituting it here, you will get the omega as root 8a. So these things are understood, so you can do that easily. That's why I just written here these answers only. Now the same method is applying here. A particle of mass m capped in potential this. Potential is given. K and lambda are positive constants. Undergoes a small oscillation about an equilibrium point. So what will be the omega, the angular frequency? Same. First you will find the equilibrium points, then the stable equilibrium point, then the second order derivative, and then substitute and put in this formula, and you will get the answer. Okay. This will be the answer, and this will be the equilibrium points. So just match them with your answers. Try to solve. Now same question means just like this question, and things are changed a little bit. The potential energy of a particle of mass m is given by this. So potential energy is given. A is greater than 0, k square is greater than 0. Angular frequency of a small oscillation of the particle about x equal to x naught is. We need to find the omega again. So I told you it is potential energy and it is potential, just same here. It's always potential energy, not potential. Okay. So in the all graphs we plotted, it was potential energy, and in the classical we denoted with this potential and call it potential. So how will you solve this? Take the minus common, then 90 minus theta will give you cos theta. So it will be minus a cos k square x. Now you have the v. Take the first order derivative, find the equilibrium points. They will be 0, or you can find them. Then again take the second order derivative, substitute the value for the equilibrium point, then you will get the omega using this formula. Mass is given, that is, so it is not given, so omega will come in the terms of mass m. So this will be your answer. Now Likewise, you can solve this question also. A particle of mass 1 kg undergoing a small oscillation about an equilibrium point in the potential this for x greater than 0 meters. The time period in seconds of oscillations is. So we need to find the time period. So first, use the same method, find the omega. Then omega is 2 pi upon t. From here you can find the t, that will be pi by 3. Now let's see some second kind of questions. Here you need to plot you can't find the values, and you need to plot directly the potential curve, and from there you have to find the answers. Let's see how. A particle moves in a potential this. For what range of energy motion of particle will be bound? So we need to find the energy range in which the particle will be bound motion, will have the bound motion. So how will you do that? Just follow the steps. First, put Vx equal to 0 and find all the points on the x-axis which gives 0 potential. So putting it as 0 and taking x square by 2 common, x4 by 4 common from here, you will find the values for x as 0 and plus minus root 2. So first on this line, plot these points. At 0 you have 0 and plus minus root 2 you have 0. First step is this, find the 0 potential points. Okay. Next step is find the equilibrium points. So how can you find the equilibrium points? By differentiating this partially. So after differentiating you will get this, and from here you will get 0 plus minus 1 as the stable or unstable equilibrium points. So let's see, 0 plus minus 1. So here and here, these are the 3 points, but still we don't know that it is local minima or local maxima. So how can we find that? So just find the second order derivative and substitute the values of these, then plus minus sign will give you maxima and minima. So let's see, second order derivative is this. At 0 it will be plus 1, so it will be local minima. So we just make the curve like this here, and if we put plus minus 1 here, then it will give you minus, so it will be local maxima, localized maxima. So at plus minus 1 we will plot like this, and here it is 0. Now you will have the whole curve. Okay, now you can just match these lines and you will get the complete curve. Now you have the curve, so you can find this energy range in which particle is bound. You can see from here that only in this region particle can be bound. So find the value of energy at this point. Okay, means how can you find? At plus 1 or minus 1 you can find the value of energy. This will be your maximum value. So just substitute here 1, it will give you 1 upon 2 minus 1 upon 4. So 1 upon 4 will be the answer here. At 0 it will be 0. So this is the energy range 0 to 1 upon 4. This will be your bound motion energy range. Same type of question you will try by yourself. For the given potential is given. Find the range of energy of particle for which motion will be bounded. So same, we have to do the same procedure. First, put Vx equal to 0. Find the all points where Vx came out to be 0. There will be 2 points, 0, 3 by 2. So this type of curve you will get 0, 3 by 2. Then take the differentiation and find the equilibrium points. Then find at what equilibrium point or which equilibrium point it is maxima or minima. So you will get this type of curve. Then this will be your energy range of the bound motion. Find the value of this at this point and this 0 to this, you will get the answer. Now there is one more question. It is little bit different but almost same. Find the range of energy of particle for which motion will be bounded if potential is this. So first you will put 0 here and you will find the values at which it is 0. Okay, then same, you will first find the first order derivative. You will find the points of equilibrium, then check whether it is maxima or minima, but this time you will get the curve like this. Means if you put the 0, then you will get the maximum value, means you will get the second order derivative as negative, means the maxima will be at 0 and it will be minima at plus minus 1 because the second order derivative will be greater than 0 here. So that's why the plot will be like this. Means if it is maximum at here, you will plot like this, and if it is minima here plus minus 1, then you will plot like this, and it is 0 at plus minus 1 upon plus minus root 2, so it will be like this. So you will just match these all lines and you will get the curve. Then the bound motion region will be, you will find the value at minus 1, you will substitute minus 1 in this equation, you will get minus 1 by 2, then 1 upon 4, you will get minus 1 upon 4. So this will be minus 1 upon 4, and you will see that in here you have the limit, but on the above the graph you will don't have any limit, means this is going like this. So this will be bound motion forever, where it is going, wherever it is going. So range of the bound motion will be from minus 1 by 4 to infinity, okay, to upside. And this region is classically forbidden, particularly this region. So particle, if it is here, then it will oscillate here, if it is here, it will oscillate here, and if it is there, then it will oscillate like this. Okay, so hope it is clear to you. Now there are 2 questions you should try by yourself. In the next lecture I will give the solution. Consider the motion of a classical particle of mass m, that is 1 unit, in a 1D double well potential. Potential is given like this. If the particle displays infinitesimally from the minimum on the x-axis, this denotes very small displacement, and friction is neglected, then which option is correct? Particle will execute simple harmonic motion in right well with the angular frequency omega root 2. Particle will execute simple harmonic motion in right well with angular frequency omega equal to 2. Particle will switch between right and left well. Particle will approach bottom of well and settle. Okay, so this is a very good question. Try to solve. B will be your answer. So try to find the solution. Now one more question we should try. Particle of unit mass is given a speed 1 meter per second at unstable equilibrium point of potential, this Vx equal to x cube minus x. What will be the speed at stable equilibrium point? Okay, so try to solve. Answer will be this, v equal to 1 plus 8 by 3 root 3 under root. So let's end today's lecture here. Thank you everyone.